Now let's do an example problem. So for the example problem, this is from the 6th edition, and it sort of shows you a cantilever beam with a point load at the left end at A, a uniformly distributed load between B and C, and we have to find the equation of the elastic curve in this portion BC. So the first thing that you do is we want to find the reactions. And again, if we want to find between B and C, we don't need to find the reaction at C. This should be B, not A. The first thing that we do is we can sum the moments about C is equal to 0. You have your point load times the distance from point C. You have your reaction at B times the distance from C, and you have your uniformly distributed load and the distance from C equals 0. So if you solve this, you get RB is equal to 4 over 5 WL. So we can do that in our next step where we do those equations of moment as well as figuring out the initial or the end result for the equation for the elastic curve, or in terms of deflection y. So you may ask, okay, what are the mini problems I could have? So we could look at this problem in two major parts. One is finding the equation of moment in terms of x. So in that case, you have to find the reaction, and then you have to use that reaction to find the equation for the moment. The other one is if you have that equation for moment, you have to find the deflection. So in that case, you have to integrate twice. You have to use the right boundary conditions to find your constants of integration. So for the first part, A, we have our point here, our reaction, and we have some portion of your uniformly distributed load. And we have our coordinates here. So you can do this in various ways. In this particular case, we're starting our coordinate system here because we want it between those 2 points. If you actually did it at the left side, it wouldn't make too much difference because the L over 2 would end up canceling out at the end. So what we want to do then is, for that particular part, we sum our moments, again, about this point J. We end up with our point load, our reaction, times the distance, and our uniform load, again, times the distance, plus the M, that's the internal M, is equal to 0. And we end up with moment is 3/5 WL x minus a half WX squared minus 1 over 10 WL squared. So this is your equation for moment. So this is your moment in terms of x. So this would sort of be your mini problem for one thing. You have a load, a beam, and you want to find the equation for the moment. So the next part, part B, is looking at, if I were to give you that equation, how you would find the actual deflection. For part B, the other mini problem, if we have our function of moment in terms of x, how do we find our deflection? So we have our equation from the formula sheet, and we have our equation for moment that we're given. And we integrate once. We introduce one constant of integration. So for this constant of integration, C1, we need a boundary condition for slope. This particular problem, we have two supports at B and C. These are rollers or pins. They prevent deflection. There's no movement in the y direction, but the slope is not zero. We can't use those. So we have to integrate then yet again. And we have now two constants of integration. So for this particular case, we do have two boundary conditions for deflection. We have at x equals 0, we have one of our rollers or pins, so deflection is equal to 0. We stick that in, we get C2 is equal to 0. That's fairly trivial. Before I said you could start 0 at point A, and then you would have x equals L over 2, y equals 0. You should end up with the same result, it's just longer. Our other boundary condition gives us C1 is 120 WL cubed. So let's go to the next slide and solve the rest of the problem. We can then take everything over to one side, so we put W on the outside as common. We take EI from the one side to the other. We end up with getting something that looks like this. So we have four terms in this particular equation. The three that we had from our solving our free body diagram for our little thing for finding our equation of our moment, integrating twice. The last one is the term that we introduced from these constants of integration. So we have now our equation for deflection. So in the mini problem, probably what the most likely scenario would be is you'd have the equation of moment in terms of x, you'd have the beam, you'd have to integrate twice, you'd have to know which are the correct boundary conditions to find the constant of integration, and then you would have equations that look like this from a selection of equations, and then you'd have to pick the right one. The other thing that you can do, let's check it. We want to check at y equals L. So what happens if we stick y equals L? We have y, we stick this y is equal to L, 1 over 10 L times L cubed minus 1 over 24 L to the fourth minus 1 over 20 L squared times L squared minus 1 over 120 L cubed times L. We end up with, we use a common denominator, 12 over 120 minus 5 over 120 minus 6 over 120 minus 1 over 120, all L squared. And you'll find out that all this equals 0. So y is equal 0 when x equals L. So this should be x equals L at the top. So what this says is my equation is correct. I get the 0 that I'm expecting. So this is one thing that you can do in your problems just to make sure what you're doing is fine.